Today we'll discuss about this UVM. Okay, one second. Yes. So UVM is nothing but actually we already seen the Verilog and System Verilog. Okay, so Verilog we are using the Verilog is the HDL. Okay, for the designing purpose we are using Verilog, and System Verilog we are using for the verification purpose. Okay, so this Verilog and System Verilog, those are nothing but the languages. But this UVM, if you consider the UVM, UVM is not a language. Okay, so UVM is one second. So UVM, so UVM is what? UVM is universal verification methodology. Okay, so this is universal verification methodology. Okay, so that means this is not a language. Okay, so this is nothing but this is a methodology. This is nothing but a methodology. Okay, so this is nothing but a methodology. It's not a language. Okay, so here so that means here so that means in we already seen the test benches in SV. Okay, suppose so if you so it is UVM, it is consist of some more built-in classes. Okay, so that means it consists of this is a so SV so that means SV we are using for test bench, but different companies will use different test benches. Okay, so to make this as standardized, so IEEE so this there is a company called Accelera. That company has standardized this one UVM. Okay, so normally it consists of some built-in classes. Okay, this consists of what? Built-in classes. Okay, built-in classes. Okay, suppose if you are doing for SoC, system on chip verification. Okay, so system on chip verification, so if you are using SV, okay, so different companies will follow different verification methodologies. Okay, so if different companies will follow different verification methodologies, so so there should be some standardized verification, no? So that means all the companies are using this UVM for verification. Okay, so UVM for verification, so this is standardized by IEEE. This is standardized by IEEE. Okay, by IEEE around I think 2002, like that. Okay, so this is about the UVM. Okay, this is nothing but it's not a language. Okay, it's a methodology only. Okay, it's a methodology. Okay, so if you see one second, yeah, so see here. So why we need a UVM? We already have the system verilog for verification, no? So system verilog will not give a particular test bench. Okay, so that means for different modules we need to write a different test bench. There is not having any standardized test bench we can't write for using system verilog. Okay, so here system verilog is a powerful hardware description and verification language. Okay, that combines with we are using OOPS concept, that is object oriented programming, that we already discussed, like child class, parent class, child class, how you inherit the child class from the parent class. Okay, and this consists of some advanced verification features. Okay, SV provides robust environment for verification. Okay, so it lacks in standardized methodology for structuring the test benches or scalable or reusable manner. So that means suppose if you want to write the test bench for ITC protocol, that test bench we can't use for other UART or other what we call other I2C protocol or SPI protocol. Okay, other PCIe protocol. Okay, you need to write separate test benches. Okay, so that means that is not reusable. Okay, that is not reusable. So that's why we are going into the another verification methodology, that is nothing but UVM. Okay, UVM is a methodology. Okay, so now UVM, universal verification methodology, comes into play. Okay, so that is the reason why we are shifting from the system Verilog to this UVM. Okay, so normally we are using the OOPS concept in the UVM only. Some concepts, whatever the concepts we studied, that we are using in the UVM. Okay, next. So what is this? UVM is a framework built on top of system Verilog. Okay, that is a framework that will be built on the top of the system Verilog that standardize the verification environment, making them more modular. Okay, so making them, so this is nothing but making them more modular and reusable. So reusable means what? So I can write, suppose if I write the test bench for I2C, so by applying some changes in the driver or like modular, so I can reuse that test bench for other protocols like UART or PCIe. Okay, that is reusable. Okay, and scalable for complex design. Okay, so these are the properties of UVM. You have modular, reusable, and scalable for complex designs. Okay, so this is the UVM framework. And evolution of UVM, if you see, from basic SV to advanced methodologies. Okay, so like in early 1990s, like normally we are using Verilog for the test benches. Okay, so in the test benches in the Verilog we already seen. So in the test benches we are giving direct stimulus. So direct, whatever the test vectors are there, we are giving direct stimulus. Okay, so test benches were simple procedural models that applies to input vectors and check the outputs. So that means in the digital, like up to FSMs, up to small modules, small designs, up to FSMs, we can write the program and we can verify the design by using the test bench. And if you go for some like SOC related or complex designs or complex IPs, okay, so this we can't write in the Verilog. Okay, so what are the issues in the this Verilog test benches means writing directed test cases manually was time consuming. Okay, so manually we are writing the test cases, no, so that will be time consuming and hard scale for complex design. Okay, so for the complex SOCs and IPs, okay, it is not suitable for those complex designs. Okay, low reusability. Low reusability means what? Suppose for the combinational circuit, suppose you wrote the test bench for full adder. Okay, so the test bench I can't use for other comparator or other we can't use for mux, demux, like that. Okay, and if I write the test bench for flip flop or if I write the test bench for counter, so I can't use that test bench for other FSM or other shift register. Okay, so that means this is low reusability. So I need to, for each and every design, I need to write separate test benches. Okay, so low reusability. Every project require new test bench. Okay, so these are the limitations or issues present in the Verilog. Okay, and coming to the system Verilog, so 1990s we are using this Verilog and directed testing. And coming to the system Verilog, this is introduced around 2005, and IEEE, they standardized this IEEE 1800 and 2005 standards. In system Verilog, I told you, no, like we are using some more concepts, and also if you are coming to the value set, so what type of data types you are using in the Verilog? Four state data types we are using in the Verilog. Okay, our value sets are 0, 1, and XZ. Coming to the system Verilog, we are using two state data types. Okay, and some more concepts are added in the system Verilog. Those are nothing but OOPS concept. So we studied about classes like parent class, child class, and inheritance, all those things, and polymorphism also, and randomization also. So randomly I can give the test vectors. Okay, and constrained randoms also. Okay, and test bench is more structured. Okay, so these, due to these properties, this is we are using for the verification purpose, but that this is not robust verification. Okay, so what are the key improvements over the Verilog means? I told you, like constrained random stimulus. So that means with some conditions we can give the randomly test vectors, test inputs to the design. Okay, so it will increase the test coverage and functional coverage. Okay, it will track the what the scenarios are tested, and also there is a concept called assertions. Okay, test benches, so this is the separate concept which is there in the system Verilog. So during this by using these assertions we can check the design properties. Okay, so these are the key improvements of system Verilog over the Verilog. Okay, so key improvements. Okay, and next, what are the limitations of system Verilog? So I told you, no, that means test bench is robust in nature. No standard structure for test bench. Okay, there is no standard structure for test bench. So every team has to design their own verification framework from the scratch. Okay, so they need to write from the testament from the scratch. Okay, and there is no guidelines for the stimulus generation, checking and coverage collection. Okay, and reusability across project was limited. Okay, that I told you, no, like for different protocols, like I2C, if I write, so that same test bench I can't use for other other protocols like SPI or UART, like that. Okay, these are the limitations. Okay, so that's why we are going into the UVM. Okay, so this UVM, universal verification methodology, they standardized around 2010. This is IEEE. So that means when this is standardized means there is a IEEE. So that IEEE they will make as universal, or they will standardize. Okay, this is the IEEE 1800.2 standard. So UVM was introduced as a standardized and industry-wide methodology. Okay, so this is industry-wide. Wherever you see, suppose like for the design, wherever you see, they are using Verilog, no? So for RTL design they are using Verilog. Like that, for verification also they are using this standardized verification methodology, that is nothing but UVM. Okay, so this combines the best features of these are the previous languages, previous methodologies, that is OVM and VMM. Okay, so from this only you got UVM. Okay, from this it taken the best features of OVM and VMM. Okay, so this UVM is developed by a company called Acelera. Okay, Acelera, and it becomes standardized around 2017, IEEE 1800.2. Okay, so around major EDA vendors, okay, EDA, electronic design automation vendors, support UVM only. Okay, so that means this ensuring the compatibility across the different tools. Okay, so that means if it is standardized and all the industry are using this UVM, means this EDA vendors also supporting this UVM for verification. Okay, so this is about UVM. And next, what are the key features of this UVM means? It's that makes powerful means modularity and reusability. Okay, so what is this modularity and reusability means? So UVM test benches are highly modular. Okay, components like driver, monitor and sequencer can be reused across different projects. Okay, so we already seen the test bench for the system Verilog, no? System Verilog test bench, if you consider, you have like test environment. In environment you have driver, base driver, okay, monitor, and all those and those things are there, no? So that we can't use for different modules, but here we can use for this driver and monitor and sequencer, we can reuse. Okay, we can reuse, that is nothing but modularity. Okay, example I told you, no, so we can verify, suppose I2C module is there. Okay, so we can reuse most of the I2C test benches for verifying SPI modules by replacing only some protocol specific sequences, some by changing some drivers. Okay, some inputs are like that, I can use this test bench for I2C module, I can use for SPA. Okay, so like that, so what happens means time will also save, no? So we can save the time, okay, and time to market, okay, design time also, like verification time also we can save by using this modularity and reusability. Okay, and next you have like mm, transaction based communication using TLM. Okay, so transaction based communication means suppose one second. Okay, transaction based communication means here we already seen like so we already seen in the system verilog. So how it will be there, like you have test and environment and generator, okay, driver and monitor. Okay, so here this generator, last class we already seen generator and monitor. So generator and monitor is given to the DUT. So how they are communicating, so last class we already seen the mailboxes, okay, or they are nothing but like a queues. Okay, so mailboxes and queues we are using in SV. Okay, so unlike that, so in order to communicate with different modules in the UVM, we are using TLM. Okay, TLM is nothing but transaction based communication. Okay, this is nothing but transaction based communication for efficient data communication. Okay, so this will reduce the dependencies between the components and make debugging easy. Okay, debugging easy. Okay, so what is a component? Component is nothing but it's like it's a class only. Okay, it's like a class only, that is a parent class like that. Okay, so this is about the transaction based class. So if you see this basic structure of test bench, okay, so if you see the basic structure of test bench, this is nothing but a UVM base class. Okay, this is nothing but what? UVM base class. So inside this UVM base class, there are like two components are there. One is component branch and next one is sequence branch. Okay, component branch and sequence branch. So component is nothing but so this is nothing but what? This is one type of class. Okay, component is nothing but this is one type of class. This will involve in the test bench hierarchy. It will involve in the test bench hierarchy. Okay, it will involve in the test bench hierarchy. Okay, so again so here if you see so that means again this UVM base class consists of UVM report object, okay, and UVM component object as a child class. So that means from here I can analyze that this is a parent class, okay, and this is child class. Okay, so this I took from the reference, that is cookbook, UVM by cookbook. Okay, so this is a component branch. Okay, and similarly if you have a sequence, so sequence branch. Okay, so sequence branch class is not involved in the test bench hierarchy. Okay, so in the sequence branch so sequence branch is a class, this is also a class. This is not involved in the test bench hierarchy. Okay, test bench hierarchy. Okay, so so that means like it's like a transaction class only. So that is a transaction class. So it have like transaction class, UVM sequence item, and UVM sequence UVM sequence. Okay, so this is having the base class, and these are nothing but the child class. Okay, so this is the basic architecture of this one. Okay, so that means here here if you see, so like so if I write the architecture of this, basically one second. Yeah, okay, so basically if I write the architecture, so it will be like you have UVM object, okay, and in this UVM object you have different types are there. Those are nothing but component class, and so you have this transaction class. Okay, so previously we are seeing now. So UVM, so component branch and sequence branch. Okay, so in this component branch and sequence branch, you have, it is divided into component branch and sequence branch. Just divided into like this. So this is UVM report object, okay, and next this is point to UVM component, UVM underscore component, okay, UVM underscore component. Again these are point to these are point to UVM test, UVM environment, UVM scoreboard, and you have UVM agent, okay, and next you have UVM monitor, okay, and next you have UVM driver, in this UVM driver you need to use a parameter. So this parameter you need to use a request and respond, okay, and next here it consists of UVM sequence space, and next UVM sequencer, okay. These all are present in the component branch, okay, and in this you have UVM transaction, okay, UVM transaction, and next you have UVM sequence item, and next you have UVM underscore sequence, you are using parameterized request and respond, okay. So this is a basic architecture of, like means some more are there, but with this 80% of UVM parameters are there in this UVM architecture, okay. UVM object is nothing but this is the base class, okay, this is the base class, okay. So this is about the architecture, okay. Suppose like how we are writing this code for, so that means this is related to code branch, and next is sequence branch, okay. So code branch and sequence branch, okay, and next so yeah, one second, yeah. So here how we are writing the like code for this this one is, so here for the UVM, how we are writing the code for the driver. Suppose if I want to write the code for the driver, so how we are writing means, so code for the driver, if you write the code for the driver, so we need to drive from the parent class, okay, okay, so we need to drive from the parent class, okay. Need to drive from the parent class, So how we are writing means, how we are writing the program means, that program I will tell you in the coming classes. Like this will be like this. So class driver, I am using a keyword called extends, okay, extends UVM underscore driver, as I am using parameterized request and respond, okay. So that means I am like so I'm driving the parent class from the parent class to child class. Okay, so that means in the oops also we already seen, no? So how you are like inheriting the child class from the parent class, you are using a keyword called extends. Okay, so like that also driver is a parent class, so that means this is a child class, like that. So and end class I'm writing. Okay, suppose if I want to write for monitor, so how I am writing class and next monitor, class monitor extends, class monitor I'm using a keyword extends UVM underscore monitor, UVM underscore monitor and end class, end class. Okay, so like this I can write for the code for the driver as well as monitor. Okay, so I need to inherit the child class from the parent class. Okay, child class from the parent class. Okay, suppose so we already seen in the SV. Okay, SV test bench we already seen, no? So what are there in the SV test bench? Suppose SV test bench, if you see, so what are there? So you have like in top there is a test. Okay, there is a test, and after that there is a environment. In the environment you have what? Generator, driver, and you have monitor, and next you have scoreboard, and next you have reference model. Okay, that we already discussed about this test bench. Okay, and so if it is UVM, so what will be there? So it will be like first test is there, same like that test, and next you have environment, and here you have what? Agent 1. Here you have what? Agent 1. Okay, agent 1 you have what? Driver, monitor, and sequencer you have. Okay, sequencer is same like a driver, sequencer is like a generator in SV. Okay, so in SV we call as a generator, but in UVM we call as sequencer. Okay, so that is same as that. Okay, and next you have agent 2. Okay, so this is agent 1 and this is agent 2. In agent 2 also you have driver, monitor, and next you have sequencer. Okay, and again you have scoreboard, and next you have reference model. Okay, so this is the difference between SV and UVM test bench. Okay, so this is the test bench related to SV, and this is the test bench for UVM. Okay, so means here you have different agents, agent 1 and agent 2. In agent 1 you have driver, monitor and sequencer, and agent 2 you have driver, monitor and sequencer, and anyway scoreboard and reference model is common. Okay, so this is the difference between the test bench between the SV and UVM. Okay, and here we'll see the PPT. 1 second. Yeah, so see here. Okay, so this we already see, and UVM component. Okay, component is nothing but what? So like UVM component, it represents the structural element in the test bench. Okay, so that is these we will see. Okay, how to create the component by using a factory. Okay, UVM factory. These all we will see. Hierarchical names automatically participate in UVM phases, and connecting via TLM ports. So this we'll see in the preceding classes. Okay, and UVM object. Okay, so this data container or non-hierarchical utility objects does not participate in simulation phases. No parent is needed. Okay, like that. Okay, so as I told you, like so this is the basic um, uh, test bench for the UVM. Okay, so first it will consist of what? Test and environment. Okay, test and environment, and next you have what? You have so coverage. Okay, and agent. You have agent. Okay, so agent, in agent what will be there? Monitor, driver, and sequencer. I told you, sequencer is nothing but it's same as a generator in SV. It's like a generator only. So if you remember that generator, it's like a generator only. Okay, that is sequencer. Okay, so in the agent, in every agent you have like monitor, driver, and sequencer. So that is given to your design under test. Okay, so this is the basic test bench for UVM. Okay, so what is this UVM agent? Okay, UVM agent is a container that is bundle of component is required to interact with particular interface. Okay, so that means so it consists of some bundle of components. Suppose this is if you are doing for SOC or any IP module, it consists of the dumb bundle of protocols like AXI, SPI, UART. Okay, agent consists of this bundle of it's like a container only. Okay, it's like a container consists of bundles of components. Okay, it consists of bundles of components that interact with the interface. Okay, that interact with the interface of DUT. So my interface, this is nothing but interface. So how it is connecting to DUT or interface? So by the agent. Okay, so it separates the UVM agent to handle transaction. Okay, so this is UVM agent. So basically like I told you, so like you have UVM driver, UVM sequencer, and UVM monitor. Okay, sequencer is same as the generator in the SV. Okay, so that is a UVM agent. So like you have you have like in this, so you have driver, okay, and next sequencer, and you have monitor. Okay, so here sometimes what happens, here driver is inactive, sequencer is inactive, monitor is active. Okay, monitor is active. So then this is total agent, this is my agent. Okay, so this is an agent. This agent we call as passive agent. This agent we call as what? Passive agent. Okay, sometimes driver, sequencer, and monitor, driver, sequencer, and monitor, both are active. All three are active. Okay, so this is I am calling as active agent. This I will call as what? Active agent. Okay, so that means here suppose if you consider one SOC. Okay, if you consider one system on chip. Okay, system on chip consists of what? It consists of processor and in order to communicate with other peripherals, you have like bus, AXA bus, AHB bus, and protocols like SPI, UART, I2C, and PCIe protocols, like that, all are there. So that means if you want to verify, so suppose UART is there. Okay, UART is there, and SPI is there, and I2C is there. Okay, so that means here this when you are using UVM, it will consider this is one agent 1, this will consider agent 2. Okay, and this will consider I2C, this will consider agent 3, like that. Okay, agent 3, like that. Okay, so if you see this one, hope you understood what is this passive agent and active agent. Passive agent means what? Some agents can be, some driver and sequencer can be inactive, and monitor only one monitor is active means I can call this as passive agent. Active agent means all should be inactive, that we call as active agents. Okay, so see here, so that means so you have types of agent, passive agent. Okay, so active agent and passive agent. Okay, so what is this active agent? Once again, so what is this active agent? An active agent contains all three components. What are those? Sequencer, okay, sequencer, driver and monitor. Okay, all should be inactive. Okay, so this actively drive the stimulus to the DUT using the driver. Okay, sequencer and driver communicate to generate and apply the transaction. Monitor observe the response from the DUT. Okay, as I told you, so like driver will generate the different test or test cases, and the monitor will monitor observe the driver. Okay, so this type of agent we call as test the DUT by applying the stimuli. Okay, so this is active agent. Passive agent means what? So passive agent means it contains only monitor. I told you, so like driver is inactive, sequencer is inactive, but monitor is what? Active. Okay, it consists of only monitor. Okay, it does not drive any stimulus. Okay, simply it will observe the interface. Okay, why? Because it will not observe, it will not drive the stimulus. Why? Because here in this passive agent, my driver is inactive and also sequencer is also inactive. Sequencer is nothing but generator. Okay, so this is inactive and sequencer is also inactive. So when both are inactive, so only monitor is active. Only monitor is active. What is the purpose of monitor? Just it will observe the interface. Okay, and it collects the data from the analysis. Okay, just it will observe. Okay, so where you are using this passive agent means, we suppose if you want to alter the behavior of DUT. Okay, or but you want to analyze or validate its activity, we can use this passive agents. Okay, so this is used for monitoring the bus transactions in multi-agent systems. Like that, we are using this passive agents. Okay, so this is about the active agents and passive agents. And next, UVM factory. Okay, so what is this UVM factory? We'll see. Okay, UVM factory. One second. Yeah, UVM factory. UVM factory. So what is this UVM factory? We'll see. Okay, suppose like suppose we already seen in the System Verilog test bench for System Verilog how it will look like. Suppose like this is my test. This is my test. Just top module. Okay, test, and here there is an environment. This is my environment. Okay, and next you have generator, and next you have base driver. Okay, and you have monitor. Okay, and this is these are connected to design and test. Okay, suppose if you want to replace this base driver, okay, with child driver. Okay, so if you want to replace this base driver with child driver. Okay, with the child driver. Okay, what you need to do? You need to like so you need to change the handle name. Okay, so you need to change the handle name. And after that, I am replacing the bus driver with child driver. Okay, I need to replace bus driver with child driver. Okay, so that is the case when you are doing with this System Verilog test bench. Okay, separately you need to write for the, so you need to replace this so you need to go into change the handle name, and after that you are replacing the base driver with the child driver. Okay, so in UVM we don't need to go inside our code. Okay, so first of all, when you want to convert this base driver into child driver, so first of all you need to go into that code, and you need to change the handle name, and you need to replace the base driver with the child driver. Okay, but in UVM you are no need to go inside our code. Okay, to change the handle name, everything. We just use the concept called factory. Just a concept called factory. Okay, that is nothing but UVM factory. UVM factory. Okay, so UVM factory. So that means in UVM factory you can change one component to other. You can change one component. You can change one component to other component. Okay, other component. So in the top level. Okay, so how we are changing means in the top level, of your factory, so no need to go into inside the code. In the top level only you are changing the one component to other component. Okay, so that means normally what you are doing, like we are creating the instance. Suppose if it is in SV, what you are doing, so like we are creating the instance of the class. Okay, by you. So how we are creating, so we already seen the classes, no? So we already using the classes. Okay, so how we are creating the classes in SV, so we need to use a keyword called what, new. Okay, so there we need to write like properties, and after that we need to write the handle. Okay, and how we are writing the instance means you need to create the object or instance by using a keyword called new. But in UVM you are not going to use a new keyword. Okay, for creating the class instance. Okay, in UVM. So this is one important point. So normally in SV what you did, that you created the handle, and after that you created the object. But in UVM, we are we are not going to use new keyword, new keyword for creating a class instance. Okay, so if you use new keyword in UVM, you cannot perform that what, overriding. Okay, overriding means what, so if you are using your new keyword, you cannot perform overriding. So overriding is nothing but what, replacing one component with other component. Okay, so that means what is overriding? So overriding, we are performing the overriding in the UVM. Okay, so overriding is nothing but what, we are replacing one component with other component. Okay, one component with other component. Okay, so that is nothing but overriding. Okay, so here if you see, like, once again, yes, see here, so there is a UVM factory. So what is this UVM factory? So this is a fundamental part of universal verification methodology that enables the dynamic creation of the object and components in UVM based test bench. Okay, so this will create what, this will create a dynamic creation of objects or components in UVM based test bench. Okay, it provides a standardized way to instantiate the verification elements. Okay, so by allowing what, flexibility, reusability, and configurability. So as I told you, like it will follow, we can use same test bench for different protocols, I2C, HPA, that is reusability, configurability, and flexibility. Okay, so that is nothing but UVM factory. So what is this UVM factory? The UVM factory is a mechanism UVM that is responsible for creating the UVM objects and UVM components dynamically. Okay, instead of traditional means what, in SV. So how you created the object, you are using a keyword called what, new. Okay, traditional method is new, creating the instances. Okay, creating the objects or creating the instances. Okay, so UVM factory uses factory registration or creation mechanism. Okay, so factory registration or creation mechanism means, I will tell you with one example. Suppose you purchase any bike or car. Okay, so what you will do, you will do the registration for the government, no? So you'll do the registration, so then only you will get a number plate, and you can you can go outside, so there is no problem with your vehicle. Okay, so like that you need to, for this component overriding and all those things, we need to go for factory registration and creation mechanism that allows polymorphism and factory overriding. I told you, so it will allows the polymorphism, and factory overriding means what? Without going into that code, so we can override, or we can change from one component to the other component. Okay, that is nothing but UVM factory. Okay, UVM factory. So what are the key features of UVM factory means? So it allows OOPS principle. Okay, like we have OOPS, object oriented programming, so parent class, child class, and we already discussed about polymorphism. Okay, polymorphism, and it enables factory override. So factory override means it will convert one component to other component. We can replace the class instances with the subclass instances dynamically. That is factory overriding. And due to this, it will creating the reusable and configurable test benches by enabling the easy modification. Okay, so this is the key features of what UVM factory. Okay, UVM factory. So what is the need for UVM factory? So I told you, overriding. Overriding means what? We are replacing one component with the other component. We are replacing one component with other component. Same thing. Same thing. Okay. So here there are like 3 steps are there for this factory or factory registration. Okay. So factory registration, that I will tell you. So first step we will discuss, and the next 2 steps we will discuss in the coming classes. Okay, so declaring the driver. How to declare the driver? Declaring driver. Okay, so there are 3 steps are there. 3 steps are there. Okay, what are those steps? We'll see. Okay, so here I'll use how I'm using like class driver. How I'm declaring driver extends. Okay, I'm using a keyword extends UVM underscore driver. UVM underscore driver. Okay, so step one. So what is step one? Step one is you need to make factory registration. Okay, so you need to use factory registration from UVM factory. Okay, so normally these classes are there in the standard library. Okay, whereas like in the UVM, these classes are, whatever these classes are there, like you have driver and monitor and all those things are there in the standard library. Okay, so first is factory registration. Okay, factory registration. So we are registering the factory registration in UVM factory. Okay, so UVM factory is nothing but this is one class present in the library. Okay, present in the library. Okay, so by using UVM factory, what you can do? By using UVM factory, you can do overriding. So what is overriding? I told you, like you can change one component to the other component. That is nothing but we can perform overriding. Okay, so this UVM factory, this is also a class. Okay, this is also a class which is declared in the library. Okay, class declared in library. Okay, so how we are making the factory registration means so UVM underscore component and registry ash driver. Okay, registry ash driver. Okay, so like this is the method to get like static method. Okay, so this is the method to get. Okay, this is nothing but we are using static method. Okay, and how I am using means UVM underscore component underscore registry. Okay, registry ash driver uh, I'm using parameterized, and I'm using this symbol. Okay, this symbol is so scope resolution symbol, no. So in the static methods we used this scope resolution method. Okay, so this is nothing but scope resolution symbol. Okay, scope resolution method get function. Okay, so that means what it is doing, it is going to return the instance of the class. It is going to return instance of the class Okay, suppose so we are using for this, I am using, this is nothing but scope resolution operator. Okay, scope resolution method. Okay, so this is scope resolution method. Okay, so suppose for registering the component. Okay, so what I am using for registering the component, for registering the registering of component, what I am using UVM underscore component I am using. So that means here one second here. So if you see here, so like this, how I am using a class my component extends UVM underscore component. Okay, I am using type def UVM underscore component underscore registry as my component type ID. Okay, I am using static function type ID get type this function and return type ID. I am using scope resolution operator get and end function. Okay, so in order to write all those these programs, I am going to use a macros. Okay, so macros, I think you have idea about macros. Okay, so here what I am doing for the component, what I am using means I am using, so that means component for factory resistance for macros, I am using tick UVM underscore component utils my component. Okay, I am using this macro for the component. Okay, so in order to write this whole program, I am using a macro. Macro is nothing but it's like a calling some macros, or we can call like small programs, no, like we are calling that standard function or like that. Okay, suppose for parameterized, I am using class my param component int extends UVM component type def my param component add width, like that I am using. Okay, so for this, so if I want to use this parameterized, I am writing 2 lines of code. So for this I can use macro parameterized component factory resistance macro tick UVM underscore component underscore param utils this underscore t. Okay, so in order to write this whole 2 lines, I can use this macro. Okay, for for cross derived from the object also, so UVM transaction dot UVM sequence item UVM sequence etc. So for this also I can write this parameterized utils. Okay, for with the help of this one I can use UVM underscore for retrieving the object. Okay, retrieving the UVM object. So this many lines I need to write. Okay, normally if I write, but by using macros I can call like this tick UVM underscore object underscore retrievs my item. Okay, suppose parameterized class is there. Okay, so I can write like this. So with the macros, I can write UVM underscore object param utils this underscore t. Okay. So this is the registration, factory registration by using macros. Okay. So this is step one. Step one is nothing but factory registration. Okay. Step one is nothing but factory registration. Okay. So this is about the UVM.